Welcome to qnawire.
So let's take our axis of rotation to be the z-axis. Therefore, the angular velocity will just have the component along k cap. So let's say the magnitude of angular velocity is omega. Now, in the first case, we have the origin to be located on the axis of rotation. So let's say the origin is 0, 0, z naught. And the point is located, let's say, at r0 z naught at time 0. So given that, we can write the position vector of the point, let's call it p, to be r cos omega t I cap plus r sin omega t j cap, which are the x and y components, and then comes the z component, which is simply z naught times k cap. And the point is moving counterclockwise around the circle. Then we find velocity using the differentiation of r, by doing the differentiation of r with respect to t, and we get this expression. And then we find omega cross r using the determinant rule to get this. Now, if you compare these two values, you see that v vector is equal to omega cross r vector. And also you notice that the z naught, or simply the C component or the K cap component of R, does not come into play in these two expressions. So this term right here does not contribute to velocity and omega cross R. Therefore, for the next case, when we shift the origin to some other value along the axis of rotation, so let's say now the 0, 0, z1, since this is again a constant, and even if you replace z naught by z1 over here and over here, they will still not come into play in the velocity and omega cross r expression. Therefore, the expressions for v vector and omega cross r vector will still be same, and therefore this condition will still hold. Now for the third case, when you change the origin to a different location of the rotation axis, so let's say now the origin is at some point x2, y2, z2, then the position vector will now change. So now the position vector will be r cos omega t minus x2, which is the origin. This is in the x direction. Then we have r sin omega t minus y2, the y component of the origin. And then we have z naught minus z2 in the kth direction. Now we do the same thing, differentiate r with respect to t to get velocity vector. So we find the expression that is similar or same as what we found before for the velocity, and we do the same thing for omega cross r using determinant rule. However, for this case, omega cross r is different now, even though this vector or this component of r does not come into play because it's a constant, but we have x2 and y2 playing their role in omega cross r. And now if you compare these two, the velocity vector and omega cross r vector, you'll find that v vector is not equal to omega cross r vector now. Therefore, for the off-axis origin, this relation does not hold.